Hello everyone, in this video I'm going to be talking about how to determine if a particular compound is going to be aromatic, non-aromatic, and anti-aromatic. So the very first thing you want to look for is obviously the compound must be a ring or cyclic, and the second thing, it needs to be planar and it should contain a continuous overlapping unhybridized p orbital, and you can also call that to be conjugated system in that particular case. So if you meet these criteria, then you're going to be in the category of either aromatics or anti-aromatics. But let's say you do not have a planar ring or you do not have an overlapping unhybridized p orbital system. And if I go ahead and say no here, then you're going to be in the category of non-aromatics. If I give you a couple of examples here, in this first one, I have these two double bonds that are conjugated with one another, but when I look at this particular hydrogen this particular carbon right there, it's actually sp3, so it does not really have any unhybridized p orbital, so as a result, it's going to be non-aromatic. When I look at the second example, I got again two pi bonds that are conjugated, but then this nitrogen is protonated where it's not sp2 anymore, but rather it's an sp3 and it does not have any unhybridized p orbital that could be used to conjugate this whole ring. And in addition to that, sometimes you may run into an issue where you have a bigger ring, but these bigger rings are actually going to be so flexible that they may not be coplanar anymore. And in that case, it's going to be non-aromatic. But then the question is, how do you know if a particular size ring is going to be coplanar or not coplanar? And the answer to that is not that easy. And a lot of time you're going to have to look at like use the molecular models to draw out the structure. And based on that, you can tell whether it's going to be coplanar or not. But typically, whenever you guys going to be asked questions in a typical organic or sophomore organic chemistry course, you will be told to assume that the given structure is actually coplanar. And that typically applies whenever you have a higher ring, like, 8-member ring or 10-member ring or even 12, 14-member rings. But, up to 6-member ring, 5-member rings, they are going to be coplanar as long as there is an unhybridized p orbital that's overlapping. Another thing I do want to talk about, when you have these unhybridized p orbital overlapping, they actually need to be parallel to one another. Like this particular system I just drawn, suppose these are your unhybridized p orbitals, and these guys are parallel to one another, and as a result, it's going to be easy for these guys to overlap. But sometimes you may run into a scenario where it's not going to be parallel anymore. Like suppose I got this guy, this orbital right there, and I have another one that kind of looks like this. So suppose this is kind of going back into the page here and this is coming out of the page. So this may not overlap properly. So in that case, it's not going to be coplanar, or it's not going to have a parallel overlapping on hybridized p orbitals, and this is going to be considered uh, not being conjugated in that particular case. So you may see that at some points, so especially whenever you have triple bonds in the ring. So we'll talk about that in an example. Now, suppose you have everything, the ring is planar and you got unhybridized p orbitals and whatnot, and I'll say yes, and then you in the category of either being something an aromatic or anti-aromatic. Now, how do you know when something is going to be aromatic and something is going to be anti-aromatic? You can use something called the Hückel rule. And the Hückel rule has given two formulas where if the number of pi electrons in the given ring, or the number of pi electrons that are actually being involved in the resonance or in the conjugation are 4n plus 2, then you are in aromatic system. And if the number of pi electrons that are in the conjugation are 4n, then it's going to be anti-aromatic. And keep in mind, n could be anything. N could be 0, 1, 2, 3, and so on. Any integers, basically, including 0. Now, enough with this, all the background. You learn more when you do examples. So I got tons of examples here I want to go over and talk about whether they're going to be aromatic, anti-aromatic, or non-aromatic. So let's start with this first one. I got this four-membered ring, and I can clearly see every single carbon here is going to be sp2 hybridized. You got two pi bonds here. So if I have two pi bonds, how many electrons I'm getting that are going to be in conjugation? That's going to be 4 electrons. So I can say 4 pi electrons. Then you're going to go back and be like, all right, it's clearly going to be either aromatic or anti-aromatic because I got everything conjugated here. But then the question is it going to be aromatic or anti-aromatic? And then I got to go back and figure out if will it fit in 4n plus 2 formula or will it fit in 4n formula. So if I plug in n to be 1, for example, and then 4n plus 2 will give you 6 pi electrons. So but we don't really have 6 pi electrons, we have only 4 pi electrons. So that means this is actually going to fit in the 4n formula. So that gives you this compound to be anti-aromatic. Okay, so let's look at this next one on the right side. So I got this double bond on the bottom there, and then I got a lone pair of electrons. So I could clearly use this lone pair in the conjugation as this lone pair is going to be considered delocalized. So if it's delocalized, it's going to be not involved in the hybridization, and rather it's going to be an unhybridized p orbital. So again, the hybridization on this carbon right there, I'm just gonna write that like here, sp2, that means this particular lone pair is gonna be unhybridized p orbital. And in that scenario, again, I got 4 pi electrons, or 4 electrons total, I can say, if you don't want to say, because it's not literally everything in pi, because at a given time you're going to have one pair of electrons to be in the form of lone pair, and one pair of electrons in the form of pi one. So but total you have 4 electrons that are in the conjugated system. So again, it's going to be anti-aromatic because it follows um, the 4n rule in this particular case. Let's look at this complicated example here. So I got this double bond here. Remember, oxygen has a positive charge here, but then still there is a lone pair on the oxygen, because remember, typically oxygen has 2 lone pairs of electrons, but here this particular oxygen is protonated. That means they used one of the electrons to make the bond with the hydrogen, but then the other lone pair is still there. So I can literally use this particular lone pair in the conjugation. It does not mean if you have a positive charge already on the oxygen, you could not use it. You could still use this lone pair, and it can go and do the conjugation system there and obviously make multiple resonance structures. I'm not going to be making resonance structure, but I'm just showing here how this lone pair could still be used in um, in the ring to create a fully conjugated system. Then how many electrons I got total here? I got 4 coming from these pi bonds here, and I got 2 coming from this lone pair. So I got 6 electrons that are being resonated or conjugated in the system, and that's going to fill in 4n plus 2 rule where n is going to be equal to 1. So that means this is going to be aromatic in that particular case. What about this next example? This next example is clearly very similar to the top one, with a difference that it does not really have a lone pair of electron on this top carbon, but rather it's got a positive charge. So that means this is still going to be an sp2, and there is going to be an unhybridized p orbital that's, carrying the positive charge technically there. So the number of electrons that's going to be in there, that's going to be making a fully conjugated system, because remember, this can kind of move down there. I'm not going to draw the resonance, but I'll just show you this moves down here, and you can create multiple resonance structures there. And then when I count the number of electrons that are being conjugated here, is going to be only 2 electrons, because this positive charge on the top carbon does not really have any electrons on it. So those 2 electrons only coming from the pi bond. And then as a result, this is going to fall again in 4n plus 2, where n is actually going to be 0. It's not going to fall in 4n rule anymore. So this is again going to be aromatic. Okay, let's look at these next guys. It's probably going to be a good idea if you can pause the session and do these on your own and see if you got those right. let's look at what's going on here. I got boron. Remember, boron is one of those compounds that can have an incomplete octet. It's got to make only 3 bonds. That means it still have an unhybridized p orbital in there. All right, and then obviously this carbon is going to be an sp2. That means it's got an unhybridized p orbital here again, and that makes this whole system conjugated because I can move these double bonds toward these positive charge or toward the boron, because boron is electron deficient atom in this particular case because it has an incomplete octet. So by having an unhybridized p orbital on every single carbon there, so these are sp2 as well, this whole ring is going to be conjugated. But now I got to count how many particular electrons are being circulated in the conjugated system, and it turns out it's only going to be 4 electrons. And why 4? Because I got 2 pi bonds. They're going to bring 2 electrons each, and it does not have anything on that carbon that bearing the positive charge, and it does not have anything on the boron either. There's no electron. It's an electron deficient. So 4 pi electrons, and as a result, it's going to follow 4n rule, and that makes it anti-aromatic in that particular case. What about this next one here? So I got this 4-membered ring, and I have 2 lone pairs on these top carbons, making those lone pairs conjugated with the pi bond on the bottom here. So if I want to go ahead and draw the resonance structure, I can do something like this, and this can come down here. And I don't want to really draw this for the sake of time, but I'll just go ahead and draw how it looks like. So when I have the double bond here now, and then I got a negative charge here, and then you can redo the same thing. You can make this go down here, and that will come down here, and you can clearly see how this whole thing is now conjugated, and it turns out you're actually using all the electrons in there that are drawn out. So I got 2 electrons from the pi bond, and then I got 4 electrons coming from those 2 lone pairs. So I have a total of 6 electrons that are being conjugated in this system. So that's going to follow 4n plus 2 rule. That makes it aromatic in this particular case. What about something like this in the next system here? I got the nitrogen, and then I got this oxygen here. Remember, oxygen has 2 lone pairs of electron like this. Nitrogen has a lone pair of electron. And if I want to make this system fully conjugated, what do I have to do? I would have to use this lone pair from the nitrogen as in a delocalized lone pair so that it can resonate with the pi bond that's conjugated with it. And I would have to do the same thing with one of the lone pairs on the oxygen. I do not have to use both of the lone pairs on the oxygen. I use only one lone pair to create this conjugated system. It's based on an as needed thing. Like if you need both lone pairs, then you use both lone pairs. But if you don't need both, you use only one. And typically, whenever you have oxygen in the ring, you're going to be needing only one lone pair to create a conjugated system. But turns out I used 2 electrons from the oxygen, 2 electrons from the nitrogen, and I got 4 electrons coming from those 2 pi bonds. So I have a total of 8 electrons here. So since I have 8 electrons here, it's going to follow 4n rule. That means it's going to be an anti-aromatic. Okay, keep moving. What about the one on the right side here? I got this 3 bonds in this left ring. They are fully conjugated. Then I got 1 pi bond that's going to be on the right ring. And then remember, there's a lone pair on that nitrogen. So that lone pair is going to be an allylic lone pair, and it's going to be delocalized based on those conjugated double bonds there. So that means I could use this lone pair in to create this whole ring fully conjugated. So when I do so, how many total electrons I got now? I got 4 pi bonds and 1 lone pair, so that makes it a total of 10 electrons. So if it's 10 electrons, that means it's going to follow 4n plus 2 rule, where n is technically going to be 2, and that makes it an aromatic compound. What about this next one here? So in this next one, remember nitrogen has a lone pair here, And remember what I said earlier that using the lone pair that are in the atom is as needed thing. If you need them to create a conjugated system, then you use them. If you don't need them to create a conjugated system, or if the system is already conjugated, then you don't really need to use those. So in this particular case, even though both of those nitrogens has lone pairs on them, you're not going to be using those because this ring is already conjugated with the pi bonds to begin with. So these lone pairs on the nitrogens are more or less considered to be localized lone pair. So as a result, I'm going to say I got only 3 pi bonds, gives you 6 electrons. So that means it's going to follow in 4n plus 2 rule, and that's going to be an aromatic again. What about this next one on the right side? This is a benzyne. So this is a typical example where you have a triple bond in the ring, and then students get confused. Do you count both pi bonds in the triple bond in the conjugated ring, or you just count only one of the pi bonds? And the answer is, again, it's as needed thing. You only need a one pi bond to create this ring, to create this fully conjugate system. You don't really need the other pi bond. And it turns out it's actually these carbons are still like sp2 technically, where the other pi bond is still going to be in the sp2 hybridization, where it's really not parallel anymore. If you go back and remember what I said earlier, that those unhybridized p orbitals needs to be parallel to one another in order so that they can create a conjugation there, or they can overlap properly. But with this triple bond, it kind of seems like it's an sp, but it's really not an sp. It's an sp2, where other pi bond it's still gonna be not parallel to this unhybridized p orbital. So you only count 3 pi bonds in there. You don't really count the other pi bond in the triple bond. So it's 6 pi electrons in there, and that's going to make it aromatic because it's going to follow 4n plus 2 rule. So this is a thing you want to keep in mind. Remember, anytime you have a ring where you have a triple bond, you don't really count both of the pi bonds in the triple bond. You only count one pi bond in the triple bond if to make this whole ring conjugated, because other pi bond is not parallel to those unhybridized p orbitals, but rather it's going to be perpendicular, where it's not going to be making the overlapping there. Okay, what about this next one here? So I got 2 nitrogen pairs. Remember, the nitrogen is going to have lone pairs, and you can see on the bottom I got 2 pi bonds there, and since I got 2 pi bonds, I can clearly see these 2 pi bonds are conjugated with one another, and since those 2 pi bonds are already conjugated, I don't really need to use this lone pair here. So this lone pair is going to be localized. It's going to be in the sp2 hybridization, but then if I count the top one, I would have to use this top lone pair actually to make this conjugated system. So this is going to be a delocalized lone pair, or another way of saying it's going to be in the p orbital, and since it's in the p orbital, I can use this to create a conjugated system. I'm not going to draw the resonances, but you can see how this can be used to create multiple resonance structures, and as a result, the whole ring is going to be conjugated. So that makes it a total of 6 electrons again, because we got 4 coming from the pi bonds, and I got 1 coming from this nitrogen lone pair. 2 electrons coming from the nitrogen lone pair. So that makes it a total of 6 electrons, and that's going to follow 4n plus 2 rule. That makes it an aromatic. What about this next one here? So assume this ring is coplanar, and everything is conjugated. So I got to count how many electrons I got here. So I got 1, 2, 1, 2, 3, 4, 5, 5 pi bonds. That gives you 10 electrons total. And since you have 10 electrons, it's gonna follow 4n plus 2 rule, and that's gonna make it aromatic, where n is gonna be equal to 2. What about this next one here? So I got two double bonds or two pi bonds, you can say I got a lone pair on the top. I don't really have nothing on the bottom here. So it seems like I'm gonna have an sp3 carbon. So I don't really have any example or much examples with non-aromatic because I had a couple of examples already on the top. But this particular one does not have a full ring conjugated because of the presence of this sp3 hybrid carbon atom. So as a result, this is going to be non-aromatic. What about this next one on the right side? You can clearly see I got a lone pair of electrons here, and then I got the boron. Remember, boron is an electron deficient where it can accept a pair of electrons, or you can use this to create a bond in there. So remember, I can technically go ahead and use this like this. So when you go ahead and create the double bond there, it's going to make this ring a fully conjugated, or um, or you can go the other way around and you can make multiple resonance structures. But turns out this will be able to create a fully conjugated system because of the presence of boron there, because it can still make another bond in there because it's an electron deficient. But when I count the number of electrons here, it's going to be 6 pi electrons, or 6 electrons that are being used in the conjugated system, and that means it's going to be 4n plus 2, and that's going to give you an aromatic compound. We can talk about this next one here. So this next one, I got this boron. Remember, it's got an unhybridized p orbital. So clearly you can use that unhybridized p orbital to make this conjugated system. But remember, the boron does not have any pair of electrons that's coming from it. So as a result, I'm only using 4. So there is an unhybridized p orbital. So I'm using only 4 electrons in the ring that are going to be creating the conjugated system here. So as a result, this follows for n rule, where n is going to be 1, and that makes it anti-aromatic. Okay, what about this next one? So this is where the issue with ring not being planar anymore comes in. Anytime you start moving away or going into the bigger rings from 6 member to like 8 members, 10 members, 12 members, and so on, you may run into an issue where the ring may not be coplanar, even though it's in a fully conjugated ring. But it's hard to tell whether when the ring is going to be uh, not coplanar or coplanar without the molecular model. So a lot of time teacher will tell you just assume that this ring is coplanar indeed. So that's what we're going to do. Assume this ring is coplanar, and from here we're gonna be looking at, okay, this whole system is conjugated. I got 4 pi bonds in there. That means 8 electrons being used here in this to create this fully conjugated system, and as a result we're gonna have 4n being followed where n is going to be 2, and that's going to give you this ring to be an anti-aromatic. Okay, let's look at this last question here. Sometimes they do ask you those kind of things. Is ask you which of the following resonance structure is going to be more stable. Obviously, I didn't really draw the second resonance, but if I go ahead and draw the second resonance, this is how it's going to look like. This lone pair is obviously Lilic. This can move down there, and this pi bond is going to move down here to create the lone pair there. So I can just copy this, and let me just move. So you create the double bond here now, and I got the lone pair here. So between those two resonance structures, which one is going to be more stable? So let's look at what's really going on. So if I focus on this top ring, would you consider that ring to be aromatic or anti-aromatic? Well, I got the pi bond and I got this lone pair that could resonate into that ring, or that makes this fully conjugated ring. So that makes it actually 4 electrons. So that's going to be following 4n rule, and that makes it anti-aromatic. All right. But when I look at this right resonance structure where the lone pair is now in this five-membered ring, and when I count this number of electrons that could be resonated into this particular ring, that would be 6. And since I have 6 electrons, it's going to follow 4n plus 2 rule, and that's going to be actually aromatic. So that means that I have one of the resonance structures creating an aromatic ring. So that means it's actually going to be more stable. So if I rephrase this question, sometimes they ask you, okay, which way you're going to have the dipole moment in this particular case. You're going to have, so there's two ways you can have the dipole. So if I go ahead and change the colors there, so I can have, since it's got the negative charge on this left resonance structure onto this top ring, I could have the dipole either going this way, or I could have the dipole going this way. It's just wherever the bigger negative charge is, you're going to have the arrow pointing that way. And it turns out you just basically look for whichever is more stable, means whichever is going to be the major contributor of the resonance hybrid. So as a result, the second one is the most stable in this in these cases. You're going to have a dipole going toward the bottom, or toward the bottom right, you can say. Okay, so this is how you're going to be looking at these resonance structures. I know in the books sometimes they only talk about some limited structures that doesn't elaborate too many examples in there. So I try to put as many examples, different varieties in there that you're going to see, mostly in sophomore organic and college organic chemistry course. If you have any questions, feel free to leave any comments in the section below.